So now we're going to learn about analysis of variance, a conceptual overview. And so, just like we're going to do some analysis on variance. And again, we saw this many times throughout the course, but we're talking about either the mean, which is a measure of central tendency. So I could have some data on each side of this. I could have like 8, 10, 10, and 12, right? And then my mean is going to be 10. And so the middle part, the measure of central tendency, the mean is 10, and I have this data which doesn't vary very much. It's not very dispersed. It's 8, 10, 10, and 12, and the mean, the average of those data points is 10, and they don't vary much. But if we had the data 2, 4, 16, and 18, the mean of that is going to again be 10. So 2 and 4 and 16 and 18 is 40. 40 divided by 4, right? 2 plus 18 is 20. 4 plus 16 is 20. 20 plus 20 is 40. 40 divided by 4 is 10. So the mean of the data is 10. Again, we have the same mean, but now the data varies a lot more. There's a lot more variance. It's more dispersed. And so we're going to do an analysis of variance to make some determinations. And we could use ANOVA, analysis of variance, to test for the quality of 3 or more population means. And so we could see if the population means are equal using this new tool, analysis of variance. And statistics is all about learning about different tools for different situations. And you learn about these tools so that if you want to measure something in some situation, you can say, we have a tool for that. And so we're learning a tool here to measure the quality, I'm having a hard time talking this morning for some reason, the quality of 3 or more population means. Data obtained from observational or experimental studies can be used for the analysis. So we could obtain data from observational or experimental studies. We want to use the sample results to test the following hypotheses. The null hypotheses would be that the means of these different populations, right? So 3 or more, the quality of 3 or more population means. And so the means of these different populations will be equal. That's the null hypothesis. And if you remember our little rule of thumb, our little heuristic for determining the null hypothesis or the alternative hypothesis, is the null hypothesis is that it's the current state, it's the status quo, there's no change, nothing has changed. And it's also where we put equality, right, is in the null hypothesis. And the alternative hypothesis is that things have changed, there's a new state, there's been change, and it's also that things are not equal. And so the alternative hypothesis here is that not all population means are equal. So if HO, the null hypothesis, is rejected, we cannot conclude that all population means are different. And this is where statisticians, I think it's another example of how they struggle with the English. So I think it'd be better just say, hey, if we reject HO, we just say that the population means are different, right? We cannot, so it's just weird. So if this is rejected, if we reject the null hypothesis, these are not equal. The population means are not equal, right? Like that's the self-evident way to say it. And e.g., for example, and we learned what e.g. was the other day, and it's like exempli gratia or something like that. We cannot conclude that all population means are different. We cannot conclude that all of the population means are different. So if we reject HO, maybe some of them are the same, and we'll put that here, some of the population means are not equal. We cannot, and we'll put this in parentheses, or we'll just put this as a subpoint. I think that's a better subpoint, because some of them might still be equal, but we can't conclude that all of the population means are different. So we'll just leave it like at that. There we go. Rejecting the null hypothesis means that at least 2 population means have different values. Okay, so that makes sense. I like that. Assumptions for analysis of variance, we'll reflect back upon these as we move through the material, but for each population, the response, the dependent variable, is normally distributed. The variance of the response variable is denoted as, sigma squared, is the same for all of the populations. So the variance of the response variable is the same for all the populations, and the observations must be independent. that'd be kind of an interesting one to have ChatGPT explain. So we're gonna like download this, and we'll say give it to me as a PNG. That's great, and then we'll go drop it in ChatGPT here in a second, and then we'll see what ChatGPT has to say about it. Let's do it now. Hold on one second. Can you please explain the concepts on this slide and provide me with an example to understand them? And I'm just going to say please instead of can, just be direct. And please explain the concepts on the slide and provide me with an example to understand them. So now I need to get the slide, just a second, and drop that in over there. There we go, and let's upload it and see what ChatGPT has to say about it. The slide explains assumptions for conducting an analysis of variance, which is statistical method. Let me just make sure I'm recording. A statistical method used to compare the means of 3 or more groups to determine if there's a significant difference between them. Here are the 3 key assumptions mentioned on the slide. Normal distribution of the response variable. Explanation: for each population or group being compared, the response dependent variable should follow a normal distribution. This means that the data points within each group should be symmetrically distributed around the mean, forming a bell-shaped curve. Example: suppose you're comparing the test scores of students from 3 different schools. If you want to perform ANOVA, the distribution of scores from each school should resemble a normal distribution. And we'll ask, what is the response variable? What is the response variable? Boom, boom. Please explain what is the response-dependent variable. There we go. Let's see what they have to say about that. Let's see what they have to say about that. The response-dependent variable is the main variable you're trying to measure or explain in an experiment or study. It is called dependent because its value depends on or is affected by changes in other variables, specifically independent variables. In the context of ANOVA or any statistical analysis, the response variable is the outcome or result that you're interested in comparing across different groups or levels of an independent variable. So the dependent variable will be test scores here. So we're looking for, in this example, right, the response dependent variable would be the test scores, distribution of scores from each school, right? So you're comparing the test scores of students from 3 different schools. The dependent variable would be the scores, and does it depend on which school you're at? So the independent variable will be the school, and it would be influencing, our hypothesis is that potentially the school is influencing the test scores. So test scores are dependent upon the school. So let's just make sure, and we'll clarify, and we'll say this here, we'll do this one here, copy that. So in the example you provided above, which I copied down below for your reference, is the dependent response variable, the test scores, and the independent variable, the school. Example from above. There we go. See what it says about that. So again, you're learning how to learn here, and look, it's excited. Yes, exactly. And I'm modeling for you how to ask questions and have that inquisitive spirit, that spirit of inquiry, so that you're like, well, let me make sure I understand this, and use ChatGPT like a tutor. And again, use the paid version. The free version produces some errors, and the paid version is really on point. It's pretty great. It's $20 a month. The dependent response variable is the test scores, because this is the outcome you're measuring and comparing across the groups. Schools. The independent variable is the school, because the test scores are grouped by the school the students attend, and you're interested in seeing if attending different schools has an effect on the test scores. So you would use ANOVA to compare the average test scores between the 3 schools to determine if there's a statistically significant difference in the test performance across the schools. So I like that. So if we come back up here, for each population or group being compared, the response dependent variable, the test score, should follow a normal distribution. And so this is what that looks like here, right? When, all of the different schools have a population mean, right? And we're going to approximate the population mean with the sample mean, and those are within the same bell curve, they're going to have this be the same population mean, right? Like these are the sample points from the different schools, but we could say with a certain amount of confidence, but they're all part of the same population mean that, or you could also say that these sample means are all equal within a certain amount of confidence. And down here, what this shows you is that when this isn't true and the population means aren't equal to each other, because the data varies too much, that these sample points must be a sample point related to a population mean that's separate, right? These populations are separate. These are 3 different schools, and they have 3 different completely distributions of test scores. Or is it that we have 3 different schools and they have the same distribution, even though they're at different locations, they have the same distribution of test scores? So that's kind of the idea there. Let's finish reading what ChatGPT has to say about it. This means the data points within each group should be symmetrically distributed around the mean, forming a bell-shaped curve. So the data points within each group should be symmetrically distributed around the mean, forming a bell-shaped curve. Suppose you're comparing test scores for students from 3 different schools. If you want to perform ANOVA, the distribution of scores from each school should resemble a normal distribution. So we need to have normal distribution of the response variable, which is also the dependent variable. That's one of the requirements for doing analysis of variance. And by the central limit theorem, we know that if we get 30 or more in our sample, our sample starts to approach the normal distribution. So I think about that. We might also, if our test scores are the response variable, the dependent variable, we could also, maybe do a large sample just to and check, does this have a normal distribution? Equal variance, homogeneity of variance. The variance spread of the data of the response variable should be the same across all populations being compared. This assumption is often called homogeneity of variance. And if I'm not sure completely, or if you weren't sure how to pronounce a word, we could come here and look it up, and let's hear it.
Homogeneity.
Homogeneity. Okay, homogeneity. So it's you might also be able to say homogeneity. Homogeneity, though, is what the computer gave us, so we'll go with that. I've heard homogeneity, I think, out in the wild. This assumption is often called the homogeneity of variance, and it's crucial because unequal variances can lead to incorrect conclusions in ANOVA. So these are just kind of like interesting to know. I assume all of the problems we're given will have these criteria in place for us doing ANOVA, but if you were out in the wild, if you were doing this on your own, you want to ensure that you have equal variance. Let's say you're comparing the average income of employees at 3 different companies. And so here, the dependent variable, well, pause the video and answer that for yourself. What's the dependent variable? What's the independent variable? All right, so now I'm going to speculate that the average income is the dependent variable and the independent variable is the 3 different companies, because we're looking to see if average income is the same at 3 different companies, or if being at a different company, the independent variable, influences your income, the dependent variable. So your income will be dependent upon which company you're at. And we could just confirm that, and say, so in this example, is the dependent variable income and the independent variable the companies. And we'll put here dependent, and we'll just add response in here. And a response is dependent on some stimulus. I don't know. Again, statisticians in English, man, they don't use English very well. But yeah, a response requires some stimulus, so a response is dependent upon the stimulus. The dependent response variable is the income, because the outcome you're measuring, and because this is the outcome you're measuring and comparing. And the independent variable is the companies, because the income data is grouped by the company the employees work for, and you're interested in seeing if working at different companies affects the income levels. ANOVA would be used to compare the average income across 3 companies to determine if there's a statistically significant difference in income between employees at different companies. All right, so we did this company one, and let's say you're comparing the average income of employees at 3 different companies. If the variance income spread is significantly different between companies, e.g. one company has much higher income variability than the others, thus this assumption is violated and ANOVA results may be unreliable. That seems like a pretty big thing. Like, we learned the basics of using ANOVA, but to really be able to use ANOVA, you have to have normal distribution in the dependent variable. Like, how do you determine that? And these would be questions that I'd follow up on with ChatGPT if I really wanted to apply this somewhere. You have to have equal variance. Like, how do you, and it's the variance spread of the data, the response variable, the dependent variable, should be the same across all populations being compared. I don't know, man. How do you determine that, right? That's a pretty big thing to determine. And again, what we're seeing here is we could just see the slide and we could just gloss over it. And we could say, okay, whatever, these assumptions. But if we really take this seriously and we want to apply this and we want to have confidence in our results, we would have to ask ChatGPT, how do I determine if, I have normal distribution in my dependent response variables? How do I determine if I have equal variance, homogeneity of variance in the dependent response variable, right, across all populations being compared? And then also independence of observations. So I'm thinking independence of observations. Well, I got a speculation. I'll tell you if it's right after we read it. The observations data points within and between the groups must be independent of each other. This means that the outcome of one observation should not influence another. Okay, so that's what I thought it would be. If the assumption is violated, it can lead to unbiased results. If you're comparing the reaction times of individuals after consuming different types of beverages, the reaction times of one person shouldn't influence the reaction times of another person. If they do, people in the same group sharing answers or influencing each other, the independence assumption is violated. Okay, that makes sense. Practical example, I love it. Let's take a look at it. Suppose you're studying whether 3 different diets, A, B, or C, lead to different average weight loss results over a period of 6 months. You collect data on weight loss from participants on each diet. Normal distribution. The amount of weight lost by participants in each diet group should follow normal distribution. E.g., most participants lose around the same amount with fewer extreme cases of very high or very low weight loss. But again, I'd be like, how do I ensure that something has normal distribution? And maybe that's a good question. How do I ensure that my dependent response variable data gathered from participants in my study, and we could call those, we have factors, we have treatments, and then I want to call them elements, but they were factors or treatments, and they were experimental units. That's what I think of people as. Variable data gathered from participants in my study, treatments applied from participants in my study, my experimental units, right? Is that what they're called, really? That's just such a weird phrase. Experimental units. So how do I ensure that my dependent response variable data gathered from participants in my study, my experimental units, how do that my dependent response variable data gathered from participants in my study is normally distributed? Follows a normal distribution. We'll do that. Follows a normal distribution. If I collect from 30 or more participants, and I'm just putting experimental units in here to see what ChatGPT does with it, and also just to start reiterating it in my own head. If I collect from 30 or more participants experimental units, will the central limit theorem apply, and will my data be normally distributed? Let's see what it says about that. Drum roll. Great question! Exclamation point. Ensuring that your dependent response variable data follows normal distribution is important when conducting an analysis like ANOVA, but there are a few things to clarify. Normality of data and the central limit theorem. Central limit theorem is a key concept that applies when you have sufficiently large sample size, typically 30 or more observations. However, it's important to understand what the CLT, central limit theorem, actually does and does not do. What CLT does? CLT states that if you repeatedly sample from a population, the sampling distribution of the sample mean, the distribution of the means of those samples will approximate a normal distribution regardless of the shape of the original data distribution, as long as the sample size is sufficiently large. So this is like the sample of this is like the distribution of doing many samples. And the distribution of sampling distribution. That's the phrase I was looking for. It's your sampling distribution. CLT does not guarantee that the actual distribution of your dependent variable, your raw data, will be normal. The raw data itself can still be skewed, bimodal, or otherwise non-normal, even if the distribution of the sample mean approaches normality. Good to know, right? So CLT only applies to sampling distribution is what I take from that. If you have a different perspective, leave it in the comments down below. Normality in ANOVA. For ANOVA, the assumption is that the residuals, the differences between observed values and group means, not necessarily the raw data, should follow a normal distribution. So the assumption is that the residuals, the differences between observed values and group means, not necessarily the raw data, should follow a normal distribution. It's an assumption. It's an assumption. If your sample size is small, we'll learn more about what that means coming up in the next video, or one of the next videos. If your sample size is small, under 30, this assumption is more crucial. For larger sample sizes, 30 plus, ANOVA tends to be robust to violations of the normality assumption, meaning small deviations from normality are generally tolerated. Whatever. How to ensure normality? Visual inspection. So you could use visual tools like histograms, Q plots, quantile plots. We haven't learned about those. Box plots, right? And check if you're approximately normal. Statistical tests, you can run formal tests for normality such as Shapiro-Wilk test or the Kolmogorov, never heard of these, Smirnov test. This will tell you whether your data significantly deviates from a normal distribution. Be cautious with very large sample sizes, as these tests may detect even trivial deviations. And transformation, if your data is not normally distributed, you can try transforming it using techniques such as logarithmic transformation, square root transformation, or Box-Cox transformation to achieve normality. So I've explored that enough for my interest. And if you want to explore it more, you can pause the video here and read that now. There you go. All right, so we left off up here where we are looking at normal distribution, equal variance. The variability in weight loss, how much the weight loss fluctuates within each group, should be similar across all three diets. For instance, if Diet A has participants losing between 5 and 15 pounds, the same general range should apply to Diet B and Diet C. And independence, the weight loss of one participant should not affect the weight loss of another. If participants influence each other's progress, sharing tips or comparing progress, or competing in a way that affects the results, the assumption of independence is violated. So normal distribution, I think you just kind of like, again, we saw down here, there's that idea of 30, even though the CLT only applies to sampling distributions, new information for me. That, always growing my own knowledge. But down here, we also saw how to ensure normality. Under 30 for larger sample sizes, 30 plus, ANOVA tends to be robust to violations in the normality. So the larger the sample size, again, here we're seeing that we start to approach normality, but the CLT specifically only applies to sampling distributions. So still there's that principle of making it 30 plus. That's a general rule that's becoming clear to me in statistics. When you do some sort of a study, you want like 30 samples or more to sort of start to get closer to normality. So normal distribution, I think we could do that. Independence, we could do that. And equal variance, I guess we could look at the data and you just look at it and see how much is it varying. You could look at the range of the data and you could see, and I don't know if there's any rules of thumb. I'm just really kind of going down a rabbit hole here. But, thinking about it, right? So the variability in weight loss, how much the weight loss fluctuates within each group, should be similar across all three diets. For instance, if Diet A has participants losing between 5 and 15 pounds, the same general range should apply to B and C. So, variance, I'd want to reflect on that a little bit more. And one question that comes up for me with variance is like, if they have the similar variance, does it make analysis of variance sort of moot? But I guess that's what an analysis of variance is measuring. but also you need equal variance in order to use analysis of variance. That's one of the assumptions. So sometimes you ask questions and you find your way to more answers, but at least you're thinking for yourself. All right, so we were looking at that slide there, assumptions for analysis of variance, and then we already saw these two slides. And this is a conceptual overview. You can see up here in the title of our slide of analysis of variance. And in the next slide, we're going to jump in and we're going to learn about analysis of variance in the completely randomized design. And we're going to learn about some of the different formulas we use. This is terminology, a lot of terminology in this module, this chapter. And we're going to learn all that, and we're going to learn all this. And so actually it's only 3 slides. And after that, we're going to jump in and we're going to see this. And eventually we're going to get to an example. And so I'm just, there's some more rules there for like how do you kind of do analysis of variance. And then the example we're going to get to, and this is all the same one, is... So this Chemitech developed a new filtration system for municipal water supplies. There are different methods that can be used to assemble the system. Chemitech narrowed down to 3 methods, A, B, and C, and wants to determine which assembly method can produce the greatest number of filtration systems per week. So this is again an example of bad English, and Chemitech has narrowed it down to 3 methods, A, B, and C, period. Chemitech, right? Because it's a colon, so it's like the colon should be like, here's the stuff, right? And it's not the stuff and a whole other sentence. So Chemitech wants to determine which assembly method can produce the greatest number of filtration systems per week. So we'll be able to do that's going to be our example that we're working towards. And we got to learn some things first before we get there. And we'll learn those in the next video. So see ya in the next video.